So of all the various, I suppose you could say, quantum-based quantum gates that exist out there, there is one in particular that I do want to focus on, which makes it actually quite curious, because it is very useful. Now, you may be already familiar with what are known as Pauli transformations from Wolfgang Pauli, right? And essentially these are things that maybe give us a bit of a change in the probability amplitudes for the linear combination representing our qubit, quite a mouthful, or perhaps giving us a kind of not operator of some sort. But in general, it changes either the probability amplitudes or the signs of the probability amplitudes or the placement of probability amplitudes. Now the question here is, what happens if we, say, attempt to take a qubit that we've already measured, we know it's either in direction 0 or in direction 1, and try to put this qubit in a superposition of some sort? What gate do we apply to it? Because clearly it still has to be a 1 qubit gate of some sort. And this is where we introduce the lovely idea of the Hadamard Gate. Hadamard Gate. Now this Hadamard Gate is denoted quite creatively as H, right? Because the people who name it want to make things very easy to understand in the process, took away this kind of very fancy name that we have here. But all things aside, as a bit of a joke, right? So we have the Hadamard Gate denoted as H. And now this Hadamard Gate can be described as a matrix. And we write this matrix as 1 over root 2, 1 over root 2, 1 over root 2, and our lovely negative 1 over root 2, a wild card in there. Now, of course, this is quite a lot to write, and actually we can simplify it down just to be 1 over root 2 multiplied by a matrix full of positive ones and a single negative one for our wild card. That is our Hadamard Gate. Now, the question is, what does it actually do to the qubit that we're applying it to? In order to truly understand what occurs, let's actually consider this in a case-by-case scenario. So, let's begin by applying our Hadamard Gate to our 0 vector. Now recall 0 here is going to be represented as, oops, this should be positive 1. Right, this is Hadamard Gate is going to be represented as 1, 0, a vector of 1, 0. And so we see here we have a case, actually a combined case of scalar multiplication with matrix multiplication. So let's do matrix multiplication first. Scalar multiplication, basically just kind of a distribution problem. So what we have here, if we write out what is occurring, we have 1 over root 2 being multiplied by 1 times 1, plus 1 times 0, which is 0, and then we have 1 times 1 times 1, right, which is 1 again, plus negative 1 multiplied by 0, which is 0, so we have 1 on the bottom as well. And so this is the result, and you might be saying, alright, that's wonderful, what can we get from this? We have 1 over root 2, and actually if we rewrite this out, you will see this is equivalent to 1 over root 2 being multiplied by our vectors representing 0 and 1. Which is interesting because we started out with this lovely little friend right here, and what we've resulted in, what we have got in return is fundamentally a qubit that is existing in superposition, because we see here that rather than knowing for sure and with definite confidence that our qubit is pointing in direction 0 or has value 0 in this case, we now can only say that our qubit has a 1/2 probability of being measured to come out to be equal to value 0, and a 1/2 probability of being measured and coming out to be value 1. Again, this relates to the probability amplitudes. And so clearly we've taken this initial qubit right here and put it in superposition. So what happens what occurs if we attempt to apply this Hadamard Gate to our vector? Or a qubit that has been measured to be in direction 1. Well, quite simply, if we rewrite out all that we have had in the past, right, we have our Hadamard Gate walking through the same exact steps of applying it to this qubit here. In this case, this qubit is denoted as 0, 1, right? We see rather than being 1 over root 2 multiplied by 1, 1, we actually see that it is 1 and I do believe negative 1 down here, which gives us 1 over root 2 being multiplied by our vector. And let me write this a little bit neater. Being multiplied by our vectors, 0 minus 1. And now you might say, all right, so, what's the big difference here? Big deal, squaring probability amplitudes, regardless of whether it's positive or negative, will still give us the same exact answer. And the answer is, well, this kind of goes back to our idea of equivalent state vectors and whether or not just negating only one of perhaps like 2 terms within our linear combination will actually do anything. And yes, it does. It changes the technical direction in which we're looking at it at. And so if we say, all right, so what does this new linear combination look like? We see again that it has a 1/2 chance of being measured to be in direction 0, or a value 0, 1/2 chance of being value 1. And as a result, we've taken this qubit and put it into a superposition. And that is actually largely what this Hadamard gate is used to do. It takes our qubit and it puts our qubit that we know, that we have a definite value of, and it puts it into a superposition of some sort. So if you are to ever encounter in perhaps like a quantum circuit of some sort, perhaps you'll see it denoted as like a line, right? This is our input here, this is our output, a single line here in this case, because it is, again, possibly a 1 qubit operation, technically speaking, right? And so you see a bit of a box with an H on it. So if you ever see that, we have a Hadamard gate on our hands. All right, so that is it for today. That introduces the idea of the Hadamard gate. If you have any questions, please do not hesitate to reach the Q-munity Tech website. And as always, stay curious and keep on learning. Thank you.